wouldn't it be nice if you could increase the fuel efficiency of your vehicle with a minimal upfront cost? My name is Brayden Harms, and in this TED Talk, we will be going over a technology that could just do this. So for this, my guiding question is Tesla Turbomachinery viable in turbochargers for low cost and high fuel economy vehicles? We'll get into what that means later. So, as we all know, CO2 emissions are rising, and they're higher than they've ever been. The EPA is also aware of this, and as a response to it, they have put certain regulations on what automotive manufacturers can make and fleet averages for their fleet. Currently, Tier 3 emissions are being put in place for 2025, and as a result of that, a lot of auto manufacturers have to increase the fuel efficiency of their fleet. So, one way that automotive manufacturers are doing this is by something called engine reduction. This is where you take a larger, less fuel efficient, but more powerful engine and replace it with a more economical, lower power engine, and you add a turbocharger to it. What this does is it has the same power, but now you just get the fuel economy of the smaller engine. So where does this power magically come from? Let's look at a turbocharger. So here you have would be a cylinder in your engine, and so when it combusts, it's going to put out exhaust. This exhaust is going to go up and into your turbocharger. It's going to spin this thing, and then this thing is going to spin this thing. And what happens with that is when this will spin, it'll compress air from the atmosphere down, and when it compresses, it gets hot, so you need to cool it, and it puts it back into the cylinder for the intake. Now, what this does is it increases the amount of oxygen that's within the cylinder, and in doing so, it creates a more powerful combustion. So, why are we just using this technology everywhere? Well, one part of it is the fact that if you're putting a larger combustion into an engine, it's going to increase engine wear. However, in more modern days, we've gotten really good with our engine technology and have made a good amount of advancements with material science. So for the most part, this is kind of negligible. So why else wouldn't we do it? One reason would be the economics of it. Does it make sense to put a turbo in a car if you're looking at it from an economical standpoint? We can create an equation that can do this. So what we have here is we have the initial cost of a turbocharger, how much it saves you on fuel, and then the maintenance cost for it. And basically, we put all of these together, it's going to say how long does it take the turbocharger to pay for itself. And for a turbocharger to be good, you need to be less than the amount of time you own a vehicle for. So if you own the typical ownership for vehicles, 8.4 years, so the turbocharger would need to pay for itself in 8.4 years. And if we look at it and run the numbers, it doesn't. So it's about 16 years until you get any gains from your turbocharger. But this isn't all lost because there is some sensitivity to this. If the initial cost was instead $939, it would fall within this region, making it 8.4 years, or if it was able to increase the efficiency by an additional 3.4%. So it kind of makes sense why there's not a full adoption of this technology. There's certain requirements needed by the automotive manufacturers. They're able to meet it with this, and they're willing to take somewhat of the lost cost in that. And there's also variances between different types of turbochargers. One thing on that. And really, if we want to completely reduce the amount of CO2 emissions we're getting, we need it to make economical sense. We need the incentive to be more than just the EPA mandates. So this needs to change. So how can we change it? Well, we can look at, if we take a closer look at how a turbocharger works here, you have these impellers, and that's kind of the heart of the turbocharger. So it's what causes them to turn when you put exhaust gas in, or what compresses it. And so as you can see, they are a very complicated shape, and the geometry is very specific. Typically, this would either be like machined or cast out of aluminum, and it's more of an expensive process than what possibly could be. So what are we going to do? I propose that we remove the impeller and replace it with a stack of just flat discs. So this is a little bit of a crazy thought, but let me get into it a little bit more. So what I mean by flat discs is back in 1913, Nikola Tesla submitted 2 patents. This was his turbine patent, which once again uses the flat disc you can see there, and his fluid propulsion patent. Now these are what's going to be replacing the impellers. So for the fluid propulsion patent, what would happen is you'd have, just like your typical turbine or your turbocharger, that fluid go in, it'd go between the discs, and it would exert a force on them, causing a torque on the main spindle there, which would then be connected to this fluid propulsion device, which works the exact opposite. If you spin the spindle, it'll create, or it'll accelerate the fluid around it. So the goal of this was to increase the efficiency by reducing the amount that the path of the fluid changes. So what I mean by that is that if you look at an impeller, the fluid's going to come in, it's going to strike against the impeller, and it's going to be shot up. This is a very sudden change to the movement, and as such, it creates a lot of turbulence. Now, turbulence is going to have an inherent loss of efficiency in this, so the theory behind this is that it wouldn't have turbulence. And the other goal of it was to be more economical. Once again, because they're just flat discs, they're incredibly easy to manufacture and would greatly reduce the cost. However, this technology wasn't really fully adopted because while in theory they should be more efficient, that's just not what it ended up being. And the efficiencies were far below than what would have been nice. However, they do have a niche market as blood pumps just because they can scale down very well, but in total, not really used apart from academics and studying the fluid dynamics of them. So how it would work, you'd have your exhaust gas go into your Tesla turbine, it'd spin up or it'll spool up, and then you'll have exhaust gas come out. You'll have a connecting spindle here, and you're going to have your Tesla fluid propulsion device pull air in and compress it and go to an intercooler just like a normal turbocharger would. So let's get into a little bit more how exactly this works. So it uses something called skin friction drag. And so what this is that when you have fluid moving across a plane, it's going to exert a small amount of force onto it as it moves across. And so that's kind of seen there, is you have the turbulent friction for a laminar boundary layer and a turbulent boundary layer. The laminar boundary layer is much more efficient at imparting energy. And you can kind of see the difference between a laminar flow, which is an ordered flow, and a turbulent flow here. So if we're looking at it, and this would be for a turbine, you'd have your fluid move in, it's going to move across this disk, imparting energy all the way across its path, creating a torque, and move into the inlet at the center. And the exact opposite is true for the fluid propulsion. If you spin this, then the fluid's going to move in the exact opposite direction because it's laminar flow, and so everything works in reverse. So let's look at how we can optimize this for a 1.5 liter inline four running at 2,000 RPM. This was chosen just because it's a very common engine for this engine reduction type of method. So how can we optimize it? There's a couple of things we can do here. The first one is looking at Reynolds numbers. So this is a very common thing that's looked at in these studies. Basically what it is it relates how fast the fluid's moving through like what size thing and a property of the fluid called kinematic viscosity. And so what a lot of researchers will do is they'll try to find what the ideal Reynolds number is. And once you have it, you can use it to design your disk gap, so the spacing between these disks, to help optimize it. And that's given by this equation here. Another thing we can do is we can look at the radius ratios. So you have the outer radius and you have your inner radius, and the ratio between them will greatly affect your efficiencies. So like here you have a radius ratio of 5, and so you'll have efficiencies up here, versus like 1, you'll have very poor efficiencies. And the other thing would be a dimensionless flow rate. This is a value correlating to how much flow you can put through a disk set. And with that, you can then calculate the number of disks you need by just finding the flow that's going through one disk and then dividing that by the total amount of flow you need. And so with these types of methods, we can create a more efficient Tesla turbine, or also applies to Tesla fluid propulsion. And so if we run the numbers on this, I chose a disk ratio of 2 because it made it convenient for putting in an engine. And then we can find that for a compressor, we need 137 disks with a 0.15 millimeter disk spacing, and a turbine, you need 94 disks with a 0.22 millimeter disk spacing. And once again, this is optimized for the 1.5 liter engine running at 2,000 RPM. So what we're doing here is we're going to put these very thin disks into very high heat for the case of the turbine and a very high stress situation. So these discs are going to be spinning about 2,000 radians per second, which is a lot. It's about like 6 and a little bit rotations per second. So very fast. When that happens, there's going to be a stress correlated with that. As you have a disk spinning, it's going to try to pull itself apart. And so that's going to be a radial stress on it. And so you can see this radial stress here as the gray line on the bottom. But as that radial stress occurs, you're also going to get a stress tangential to that as it basically increases its perimeter. So if you use 2 pi r, then you're going to try to increase that. So you need to increase your rate, like I want to say perimeter of that as well. And so that's going to be your tangential stress. And so if you combine these two stresses using something called a von Mises stress, we get that blue line here. And so very high stress, very high temperature. So now material choice becomes very pertinent. And so we can look at a couple of different things here. We can look at Inconel 625, which is a nickel chromium alloy. Very common in these high temperature and stress situations. We have stainless 309, which is a high temperature stainless. And these are the two we're going to be evaluating for turbines. And this is aluminum 7075, which is a just common aluminum that's easy to machine and cheap. So if we evaluate these, we can find that Inconel, this would be the stresses for each of them. They're slightly different because of their densities. And then we can correlate that to what's called a safety factor. And we find this by dividing the yield strength of the material by the amount of stress applied to it. And so we can find Inconel 625 is 2.5, which is good. Stainless 309 is 1.32, which is acceptable but lower than what would be standard. And aluminum 775 is perfectly fine, mostly just because the temperature is not applied to it. And so from this, we can choose that we want to do Inconel 625 with aluminum 775. Inconel 625 is slightly more expensive than stainless 309, but as you'll see later, it's worth it. So what does the performance of this all look like? So we have 2 disk stacks here, and if we can find the cost for those, we can see that it's going to be about $32.24 for the combined disk stack. Now this is very good. Now if you think about going back to the impeller before, if you can build an impeller for that cheap, I'd be very, very impressed. However, there is some nuance to this. While it is cheaper, that doesn't mean it's better. So what can be done here is we can find the amount of torque that's being generated by the turbine, and we can find the rotational mass of the disk set, and we can calculate something called turbo lag. Turbo lag is the amount of time it takes for the engine to get to the pressure, inlet pressure that it would need. And so with this very rough calculation, we can graph turbo lag. And so if we are running at, like, let's say 600 RPM, we can say it's only going to take half a minute to get up to pressure, which is a very long time. And like the pressure is here in the blue as well, so the pressure is also low. So it's going to be about 30 seconds to get up to like 5 psi, let's say. And once again, this is also a very rough number and not accurate at all. And we can graph this for different RPMs, and we can see that typically like it's not really going to get above like 3 seconds, which would be considered very poor for a turbocharger. And so what this would mean is that if we can't get the pressures that we need, it's going to reduce the efficiency of it, and it could just make it not a viable technology at all. And so there is a lot to be said about that. So in total, would I suggest Tesla Turbomachinery being used in turbochargers? Well, there's kind of a lot to that as well, because yes, they are a lot cheaper, but the performance is dramatically less. And so they can't really even be considered, they're in very different categories just because they're different use cases. Typically, turbochargers would be considered a performance item, and the Tesla Turbomachinery would just not be in that market at all, so it's exclusively for the low-cost, high-fuel economy vehicles and trying to put more into them. And the other thing would be, there would be concerns about like warping and the stresses applied to it. You're going to go through a lot of thermal cycles with the disks. And so because of that, warping can occur, and that could cause errors further down the line as well. So all in all, it does need to be researched more because initially my conclusions did see that the technology could be promising just because of the greatly reduced cost, but more research is needed because of the fact that there are some errors there as well and how accurate that would actually be. So testing would need to be done to conclusively say if they are a good or bad idea. However, if we were able to get this technology to work, what it would mean is that we'd have a dramatically reduced cost to it, so automotive manufacturers would be more incentivized to put into vehicles. And if that would be done, it would reduce the emissions greatly on the road. Typically, turbochargers can reduce cars, or increase the car's fuel efficiency by 14%. So in theory, this would dramatically reduce the amount of CO2 and help solve the problem of the excess CO2 in our atmosphere. So thank you for listening to my TED Talk.